Okay. So hi and good afternoon, everyone. Thanks for joining us today at this different time. Before we start the seminar, we would just like to announce a reminder for the next AFMC, which will be held in December in Canberra. The call for abstracts is currently open and I believe is due soon. So please check afmc2024.org for the dates and for further instructions. Our talk today is a very interesting one, so it's a pleasure to introduce Professor Elie Bou-Zeid from Princeton University. He is an expert in geophysical fluid dynamics and atmospheric sciences. His research is broadly focused on measurement and modeling of mass and energy transfer in the lower atmosphere, with applications to urban environmental quality, building energy efficiency, and renewable energy production. He's the editor of the Journal of Atmospheric Sciences and has served as the founding director of the Metropolis Project for Urban Technology until 2022. Thank you, Elie, for joining us and accommodating the time. And it's a pleasure to have your talk.
Thank you, Azadeh, for the introduction and for inviting me to give this conference, this webinar. So if anyone has any clarification questions they want to ask, please, just speak up. I'll be hiding the video so I can see my own slides. But please, I hear you, so interrupt me if needed. And at the end, we'll have some time to chat, of course. So today, I decided to give a talk on a topic that has fascinated me for quite a while, which is basically flow over very rough walls. And for me, very rough walls, as you will guess very quickly by looking at this image, are mainly cities. I'll focus more on the fundamental physics, and then I'll touch a little bit on parametrizations. And this is mainly the work of my PhD student, Chili, and my postdocs, Maida Riaguno, Monizza, and Lucia Stein-Montalvo, and with other collaborators and students that you can see here. So the cities that we live in are quite fascinating. They are really a new Earth system that we are creating ourselves. Some call it the urbisphere. I sometimes call it the metrosphere. This is Shanghai from 1980 till about 2010, and you see the very rapid change in the landscape and the geometry and the topology of the surface. And obviously, you can imagine that this is going to alter the airflow and turbulence, but it also is changing the pollution, the temperature, the hydrology of these surfaces. So it's really creating a new environment that's completely controlled by human design and activities. And we need to understand this new Earth system because today cities consume about 75% of the energy that we use worldwide and emit about 80% of greenhouse gases, although today only 55 to 57% of the world population live in cities. By 2050, that fraction will go up to 70%. And as we face problems related to climate change and resource use, these grand challenges are really going to be overcome in cities if we manage our urbanization and urban design correctly, or not if we basically fail to think about how we build our cities of the future and retrofit existing one. So cities are important for every grand challenge that humanity is faced. Obviously, fluid mechanics in the city is a big part of the challenge, how to design and understand flow and transport in cities. And just like with wind turbines, you can look at this at the turbine scale or the building scale. You can ask, if I put one cube in a flow, what will happen? So the fluid mechanics at the building scale are already fascinating. So for example, in the figure on the left, actually, let me change this a little bit to a laser pointer. So in the figure here on the left, you see that the flow is diverging vertically, going up and going down. And if you look on the right, this is a top view, so the flow is diverging laterally. And so you see flow divergence in the front and flow recirculation in the back in the back regions behind the cube here. Now, if you take a side view simplistically, you can say that the flow is going to diverge roughly about 2/3 of the height of the cube, with 1/3 going up and 2/3 of the flow going down. As it goes down, it reaches this corner, it gets pushed back basically. And as this backward flow meets the incoming flow, what will happen is that you'll have at the bottom, you'll have the formation of these horseshoe vortex at the base of the cube. And higher up, if your cube is tall enough, you're going to basically get a vortex shedding as you would expect from any cylinder in a cross flow. So again, these are at the building scale. You're already also going to have TKE production in the wake. And if you add basically heating, solar heating to this problem, you're going to get some hot facets that are going to create some buoyancy, and you're going to get some buoyant TKE production, or sometimes even destruction. Now, from the building scale, you can go to the neighborhood scale. That's a bit like thinking, if you want, about a few wind turbines, and when you start thinking about, for example, wake interaction. Here also, when we have more than one building, we have to think about wake interaction. So if they are very far from each other, we basically call this the isolated roughness flow regime, where basically the wake from this front cube does not have a big impact on the one in the back. Here we have a wake interference regime, where this wake is very important to the flow over this cube. And when they get very, very small, you don't even have a wake anymore. You have the skimming flow going above the cubes, and some recirculation regions in between the cube. And if the buildings are very tall, you can even have this first circulation driving a counter-rotating circulation, and so on. So this is, again, at the neighborhood scale. At the neighborhood scale, an important question is, what kind of mean wind profile do you get? Obviously, when you go far above the top of the building, the top of the building is at 1 in this plot, you're going to recover a log low. We're going to talk about this a little bit. But as you dip into what we call the urban canopy layer, where the flow, where the buildings are, or the roughness sublayer, which is the layer affected by the presence of the building before the flow homogenizes in the ISL, then here we know that, for example, sometimes the flow departs from logarithmic, and we sometimes model it as an exponential flow that then merges into a logarithmic flow. Now, you can go even larger, again, to give the wind turbine analogy. Now you're looking at the farm scale, and you can ask what happens to the fluid mechanics when you start looking at the whole city. And again, there's a set of very interesting questions there as well. So, for example, in this paper, we looked at what happens when you have a city that is hotter than the surrounding with a weak inflow. In this case, you're going to have a thermal circulation that you can see here. The flow, this is the temperature, so the flow goes up and creates this thermal circulation, and it's mildly tilted by the incoming flow. And as you make the flow stronger and stronger, you basically completely obliterate eventually this thermal circulation, and you get eventually this regime that we call the plume regime. This we call the bubble, where basically there is just advection of pollutants and heat from the city. So these are kind of the three scales of looking at the city. So today I'm mainly going to talk about the intermediate scale, which is the neighborhood scale. The building scale, typically, we only study it if we're trying to design an individual building or for validation. The city scale has a lot of interesting questions, but a lot of my talk is at this intermediate scale. And this intermediate scale is what I call a very rough wall. Now, there is quite a bit of literature. This review paper by Javier Jimenez is a great example of turbulence over rough walls. So what is different when we talk about cities, and why do we have to differentiate between cities and typical rough walls that are studied in the classic literature? Well, let's start first with the scale of the roughness. So in this paper, Javier directly tells us that basically he's focusing on flows where the roughness length K over the depth of the boundary layer delta is less than 2.5%, and K plus is about 50 to 100. Now, typically, when we are interested in cities, K over delta can be up to 10%. So buildings can be 100 meters or taller, and the depth of the boundary layer, the atmospheric boundary layer, is about 1 kilometer, measured in K plus, that's 10 to the 5. So that is basically a very different regime. And here the roughness is protruding well into the, well beyond the buffer layer and well into the inertial sublayer. Also, in typical rough walls, we are interested in what the roughness does to the rest of the flow. We typically don't care about what happens in between the roughness element. And cities, what happens between the roughness elements is where we live. So that's very important. So we're really interested in the details of the flow inside the canopy and the roughness sublayer. And we're interested then in, for example, how does the roughness affect airflow, heat exchange, and chemical transport in these flows. So it's different from the classic rough wall literature. So obviously, an important question is how much drag does a building or a set of building apply on the flow? So that determines, for example, the mean velocity profile has influence on the turbulence production and so on. Now, this is basically what I won't like to call the easier problem, even though it's not very easy. But you can imagine if all your buildings have sharp edges, they're like this flat plate right there. And this is from the book of Lex Smits. And in this case, for the flat plate, the drag coefficient is constant at a large range of Reynolds number because the separation points are always at the corner of the plate. When you go to cylinders or ellipses, the Reynolds number starts dictating where separation happens. So CD is not really constant with Reynolds number. You get the drag prices and other things. But overall, it varies, let's say, by an order of magnitude. And so if the buildings are round, the drag coefficient might change by an order of magnitude or so, depending on the shape of the building. However, because basically the Reynolds number is so elevated, pressure drag is completely going to dominate the drag, and you can hope to get basically some sort of Reynolds number independence very quickly when you look at the drag problem. Now, one challenge in urban flows is we're often also interested in the transport of scalars, primarily heat, but also, let's say, water vapor pollutants and so on. And so for the heat transfer problem specifically, when you have a heated wall and you want to study basically the heat exchange between the city and the atmosphere, in the heat equation, there is no pressure term. There is no pressure moderated heat exchange. So the heat exchange is always happening via viscous or molecular transfer and radiative at some level, but mainly viscous and molecular transfer in the basically viscous sublayers that are surrounding the roughness. And the challenge with that is that, I mean, you can expect that if the viscosity and molecular diffusion are important, then this is never going to be a Rayleigh or Reynolds number independent problem. And you can think about this more differently. So we said that CD for the drag may become Reynolds independent. The equivalent for heat is the heat transfer coefficient or the Stanton number that we typically can write as Nusselt over Reynolds times Prandtl. And you quickly can see that the Stanton number is going to become independent if and only if Nusselt scales like Reynolds to the 1. At the typical Reynolds numbers that we observe for cities. Now, you can take basically any type of heat transfer problem, any setup, and you're always going to find that the Nusselt number does not scale with Reynolds to the 1 under almost all circumstances. So typically, Nusselt scales with Reynolds to some power m. That power m could be 0.5, 0.8, depending on the setup and whether the flow is turbulent or laminar, but it's never 1. And not only that, typically this m actually itself is a function of the Reynolds number. So it's not that the slope on this graph where we plot Nusselt versus Reynolds is not a constant, is not equal to 1. It's actually also a slope that varies depending on the Reynolds number. So this makes the problem pretty much harder. The absence of an equivalent to pressure drag implies that Reynolds number independence is not attainable. Nusselt increases with RE, but M remains smaller than 1. So you can expect that the heat transfer coefficient or the Stanton number will scale with Reynolds number to some power P that is actually a negative number. And this is going to become important when we later on talk about the heat transfer coefficient between an array of cube and the atmosphere. That is, for example, represented by this equation. If you basically assume there's a log law for velocity and temperature. And this is also going to become important as we try to relate the momentum roughness length to the scalar roughness length that we need basically for temperature. Okay, so the scalar roughness length is what you would use in a log law that is formulated for temperature as a function of heat flux at the wall. Now, an important question is when, okay, so these are the challenges and we want to address them. We can do experiments, we can do DNS, wall resolved LES, or wall modeled LES. And the question is, which numerical technique do we use for simulation? And so this boils down to which kind of you know, what I guess school of you know, school of thought do you adopt, or what scares you more? Is it the error related to extrapolating from a lower simulation Reynolds number? You can do a very accurate DNS or wall resolved LES and get some results at a low Reynolds number, and now you have to extrapolate them to a high Reynolds number. That is going to introduce some error. Or you can do a wall modeled LES, where basically you can match the Reynolds number, but now you have to contend with the wall modeling and SGS closure errors. So again, depending on what scares you more, you'll, I guess, adopt the other approach that you know, you think will yield lower error. Now, for me, I mean, I think you know, a main problem is that the RE extrapolations errors are irreducible unless you use more grid points. So unless you really can increase the numerical resolution, there's not much you can do about the RE extrapolation errors. You can create a model to predict them potentially, but then you're trying to model and reduce the error. On the other hand, with wall or subgrid scale modeling error, at least we can do some, basically try to refine our wall and subgrid scale model in the hope of reducing these errors. So as you can guess, I will adopt the second approach in the rest of the talk. So our LES code, I'm not going to delve into it much. It's a pseudo-spectral code in the horizontal direction. We use center difference in the vertical direction. We use a uniform Cartesian mesh with an immersed boundary method, representation of the buildings. We use a Lagrangian scale-dependent model for subgrid scale modeling, and an equilibrium wall model based on the log law. And again, all the detail and validation for momentum and heat transfer are in these two papers. In this paper at JCP, we try to work a lot to reduce the Gibbs phenomenon because we have pseudo-spectral with immersed boundary method. And in this one, we kind of validate and take a look at the physics of this model. I don't want to delve too much and waste too much time on LES. I'm happy to answer any question. I want to jump into, okay, believe me or check this paper that the LES that we use actually is useful and accurate enough to answer the question. So what kind of questions are we asking? So first, we're going to look at how the geometry or the density of the building affect the flow. And typically, this is a very nice paper that is now actually 21 years old already, about basically flow and dispersion in urban area and the annual reviews. And typically, two parameters that we like to use to describe the density, they're not sufficient, but they are necessary and useful, is what we call the planar area density, which is simply the fraction of the lot that is covered by buildings. So area of roof divided by area of building, and the frontal area density, which is the area of the buildings projected normal to the flow. So that's the area that's obstructing the flow, divided again by the total land area. So in this paper, and in one of the papers that I'm going to talk about, we try to basically vary lambda p and lambda f separately. Typically, they're varied together. basically as basically you can see here, keeping lambda p is equal to lambda f. But and we did those simulations where we keep them equal to each other and we vary them up and down. But also we wanted to do simulation where we keep lambda f constant at 0.25 and vary lambda p alone. And most of the plots that I have time to show you today are from this third set, where we leave lambda p constant, so the total area covered by the building is constant, but we change the shape of the building. The flow is coming from left to right, so we're going to make them either very wide or basically very slender, keeping again actually the slender is the black, sorry, not the orange. Yeah, so the slender is more like the black shape. So we're going to vary basically the aspect ratio of the building to change lambda f. So this is kind of the numerical grid. The buildings cover only 1/8 of the domain height. The domain extends to 100 meters, and the details are in this paper. So the first thing we observe is that actually when you, again, holding lambda p constant and varying lambda f, is that you get really a transition in the nature of the flow. So let's first look at the black line. This is the shear length scale. So this is like the vorticity thickness divided by the height of the building. So when the buildings are really slender, you notice that LS is larger than H. So H, the height of the building, is the smaller length scale, and as a result, it kind of controls the flow and controls turbulence production. And what that ends up giving you is that basically the flow ends up looking pretty much like a wall-bounded flow in terms when you look at the profile and the characteristic of the turbulence. Again, the buildings are very slender, and as a result, they don't put a lot of drag on the flow, and you get something that looks like a wall-bounded flow. Now, when you make them wider, you obstruct the flow more. And this basically becomes similar to obstructed shear flow that Marco Ghisalberti, who's actually at the University of Melbourne, basically talked about in this JFM paper. And here what will happen is that essentially you go from something that looks like a log row to something that looks like a mixing layer where you have a U1 and U2, and the mixing and turbulence production at the interface is controlled by the shear. When this shear length scale drops and becomes smaller than H, and so as a result, the mean profile and the nature of the turbulence that is generated it changes. Now this is okay, so the turbulence is changing, but this has also actual implication on the flow and the interaction between the roughness canopy and the flow. So for example, you can look at this RUW, which is a correlation coefficient between U and W. So you can think of this as a momentum transport efficiency by turbulence. So when you have a wall-bounded flow, it's actually pretty low. And when you transition to something more like an obstructed shear flow, that efficiency actually more than doubles, increases significantly for momentum. Now, you can do the same thing for heat and ask the question, how is heat transfer affected? In this case, heat is a passive scalar. How is heat transfer affected by the change in the geometry? And as a result, you can look at our theta W, so the effectiveness of heat transfer. In this case, it actually starts at again, starts slow and increases very fast and then decreases a little bit as you continue to obstruct the flow more. And as you look, now you can look at the relative efficiency of momentum over heat transfer. This is in blue, and you can see that for wall-bounded flow, the ratio is close to 1. So we kind of have a Reynolds analogy where momentum and heat are transported in the same way or with the same efficiency. And when you go to obstructed shear flow, the transport of heat becomes almost twice as efficient as that of momentum. So again, there's real implications on the structures of the flow and the efficiency of exchanging heat and momentum between the roughness sublayer and the flow. So this is all about the turbulent fluxes, but turbulent fluxes are not the only game in town when you have rough walls. So we have to also think about the dispersive fluxes. So what are dispersive fluxes? So anytime you have a transfer of a scalar, a quantity, you can write it at any point in time and space as w times t. So this is just the advection of t by the velocity w in the vertical direction. Now, if you want to get the average of that flux over time and in space, you have to first average it in time, and averaging in time is denoted by an overbar. And remember, because the flow varies in space, my Reynolds averaging has to be done in time. So that's the only allowable way to, or this is the only way that ergodicity can be applied. So you have to average in time. But then after you average in time, you're going to get a flux that varies in space. If you are interested in kind of regional or neighborhood scale measures, you want to also use the brackets, which here denote averaging in space. And you can take this and you can decompose it into two terms. The second term, you'll be familiar with it. Prime is the Reynolds perturbation. So W prime T prime bar is the Reynolds flux, heat flux in average in time, and then you can bracket it so you can average in space, and that gives you the turbulent flux. But this term also becomes important. So this is the average W in time and the average T in time multiplied by each other. So this is a product of mean quantity, but then it's average in space. So this is the spatial correlation of the Reynolds averaged fields of W and T. And usually, if you have a flat wall, W bar is 0, and that term goes away. But when you have a rough wall, that's not equal to 0. What does that mean? So to kind of visualize this a bit physically, let's take this term. And we can also write it as W double prime times T double prime, where this double prime is the perturbation of the temporal average from the spatial mean. So this is W bar minus W bar brackets. And this is a quantity, W double prime and T double prime, that's going to vary in space, but not in time. And basically, this is the mean flow of W. So the streamlines are the mean field of W, and the colors are, in this case, the mean field of U double prime, not T double prime. But you basically see that there's a correlation between W double prime and U double prime that is going to generate the dispersive fluxes. Let's delve more into what that physically means. So this is, again, the mean flow. This is all average in time. This is the circulation. And what you will observe here is the flow is circulating. And as, let's start at the bottom. As it approaches the upwind face in this canyon, it's going to slow down and go up. So this is an upward flow of slow fluid. So basically, this is kind of, if you want, contributing normally to the momentum flux. So this part is going to create a downward momentum flux as you expect. However, as the flow recirculates, it's going to accelerate again. The flow is going to accelerate in this region. However, as it approaches the next building wall is here, it's going to again slow down because it's feeling the pressure increase. It's feeling the stagnation pressure of the upwind building. So it slows down, and this creates a basically a downward flow of low momentum, U momentum fluid. And basically, this is a circulation that's transporting slow fluid downwards. So this is kind of offsetting this component and creating, if you want, a counter gradient flow. And so there's a competing effect at the leading and trailing edges when it comes to U. This is the dispersive flux pictures for momentum. Now for heat, again, we don't have a pressure term. We don't have a stagnation pressure equivalent for heat. So if the buildings are hot, when the flow goes goes towards the upward or the upwind building, is gonna get in touch with this building, and basically it has been heated by the ground, so it's transporting hot fluid upwards, which in this case, because the surface is hotter, is again a down gradient flux. But then as the circulation turns and approaches the downwind building, it cannot heat up remotely. It has to get in touch with the building and pick up that heat via the wall model in LES or via viscous diffusive transport in the real world. And it's not done fast, so the flow remains cold and it's transported downwards. So this is transporting cold fluids down, which is again a down gradient flux. So in this case, on the windward and or the leeward and windward side, the dispersive fluxes are in both cases contributing to a down gradient flux of heat, which means that the dispersive flux actually also transport heat much more efficiently than momentum. And the physics between momentum and heat transport by the dispersive circulations are quite different. So this is also consequential because dispersive fluxes become very important depending on your geometry. So this is kind of the fraction of dispersive over total and turbulent over total fluxes for momentum and scalar and for different geometries. We can delve into the details, but the bottom line is dispersive flux is sometimes larger than turbulent flux inside the canopy. Near the canopy, dispersive flux is always important for all geometries and for both scalars and momentum. So dispersive flux is a consequential and important quantity to basically quantify and model. Now, so we have momentum and heat fluxes that are basically affected by turbulence and dispersive means. One important question is if I do RANS or LES or even some wind tunnel experiment, a very important quantity to infer is basically the ventilation. So I'm interested in momentum transport and heat transport, but I'm also very interested in the canyon ventilation. So this basically will dictate, for example, how much of the pollution is exchanged or ventilated from the canyon to the free air. So if you take this dotted fuchsia line, actually, you can ask the question of what is the air exchange rate across the top of the canyon. And you can simply formulate it as basically the total amount of air that's leaving the canyon. So in an LES, you can define W plus. So W plus is a positive W that's kind of air leaving the canyon. And you can average it in time and you can integrate it in space. And basically, you then multiply it by the area. And this becomes the area times the positive W quantities that are now averaged in time and also averaged in space. And this is basically what we call the air exchange rate. And from LES or DNS, you can basically compute it exactly because you have W at every point in time and space. So you can take all the W pluses, the positive value, and then average them in time and space. So it's very simple. You can also realize that basically if you just take W and average it in time and space, it's equal to the average of W plus the average of the W minus. Think of a time series. You're taking the positive values and negative values. If you average them separately and then you sum them, you get the average of this quantity. And if you have an infinite 2D canyon, or if you have periodic domain or homogeneous canopy, typically this quantity is zero, but that's not essential in general. In this case, it was important for us to realize that this is zero, because if you realize that this is zero, then basically you can take only W plus and write that W plus is actually W is the time and space average of the absolute value of W over 2, right? So again, the absolute value so this quantity is the sum of the two. And if you take only one of them, then they are equal according to this equation. And so this quantity becomes the average of the absolute value over 2. This is going to come in handy. But if you can write this, then you can basically also write that the air exchange rate here is also half A times the absolute value of W average in time and then average in space. And sometimes also, instead of quantifying the air exchange rate in terms of of meter per second, we want to divide by the volume of the canopy and then express it in a time as a time scale or inverse time scale in second minus 1 according to this equation. Now, if you basically can use this equation, this is actually quite useful because unlike in LES or DNS, if you're doing RAS or if you're sometime doing, let's say, experimental measurements, you cannot obtain the velocity at every point in time or space. However, if W has a normal distribution, so if W is Gaussian, then the absolute value of W has a distribution that's called the folded normal distribution. So you take the W, which is in red, and you literally fold it around 0. So you fold it to the positive side, and you obtain this green line, which is the folded normal distribution. And the relationship, the moments between the relationship between the moments of the original normal distribution and its folded counterpart are actually related directly to each other. So you can basically take W, the mean in time of W absolute value, and express it in terms of the mean of W and the standard deviation of W. And as a result, you can write an estimate of the air exchange rate using this folded normal distribution model, given these quantities where basically you only need W bar and sigma W. Now, this is extremely useful because now you can do RANs with some basically some second order closure that gives you sigma W, or some lower order closure where you can model sigma W from the TKE, and you can basically estimate that air exchange rate from RANs or from measurements at multiple points in your wind tunnel, where at each point you can only obtain W bar and sigma W. Now, the question is W normally distributed? It is. We've done this verification multiple times. If you look at the distribution of W at various points in the domain, the bulk of the points are normally distributed. Of course, you get the fat tails, and that's kind of important for some applications. But the fat tails are so improbable and so rare then that from a basically air exchange rate and ventilation perspective, those events at the tail that depart from Gaussian are not important. So if that is the case, then indeed the folded normal distribution model is a useful model that actually lumps the dispersive and the turbulent exchanges together. And when we compute, for example, the air exchange rate from LES for flat roof or pitched roof or round roof, or with balconies or whatnot, the air exchange rate from LES and from this folded normal distribution model are very well captured. Some other models in literature are not captured very well. And also, this model allows you to directly distinguish between the dispersive component and the turbulent component of the air exchange rate. Now, here you see that we're simulating pitched roof and round roof. So in fact, these simulations are not done with our LES. They're done with Fluent because it can handle complex geometry better than our LES. And these are the two papers where we basically report some of these results. Finally, if you want to improve the ventilation of your urban canopies, with these tools now you can start designing cool ideas or cool things. For example, in this paper that was just published, we use Kirigami ideas or Kirigami inspiration to improve urban ventilation. So Kirigami is like origami. So origami means folded paper. Kirigami in Japanese means cut papers. So you take a paper, you cut it in certain patterns, and then when you strain it, it deforms into a 3D form. And this 3D form starts to look like louvers or basically little wings, as you can imagine here. So if you, for example, deploy a Kirigami over your street or over your streetery, in this case, streeteries are these like outdoor structures that are basically that popped up during COVID to allow you to dine outside. You basically can create these patterns, and this is kind of, we did a wind tunnel experiment and a Fluent simulation to basically show that depending on how you design them, you can actually improve ventilation very, very significantly. This is kind of showing you the velocity u being the wind being trapped or captured by the kirigami and brought into the building and then exiting the building at that tail of the building. And again, you can do basically, and the kirigami don't only allow you to ventilate, they also allow you to shade. So you can use them to shade and ventilate. So let's talk a little bit about parameterization for the last few minutes, because this is at least in my title, so I need to touch on it. So first, let's differentiate between the micro scale and the macro scale. So in our LES, we have a wall model that's based on the log law, as I told you. So for that model, we need to impose the roughness length of momentum and scalar for each individual facet. Those roughness lengths are related to the indentation and the little texture of the walls and buildings. And this is basically what we call the micro roughness. This is unresolved in the LES. This is imposed by our wall model. And so we can't say much about what's happening at the micro scale. However, when you look at the macro scale, then you can also take a bunch of cubes and look at the flow above them. And now you can basically define a macro Z0 for momentum and scalars. And this is basically, again, this is the log region above the neighborhood. And if you have a log region, you can basically determine the intercept of the log law and basically determine the roughness. Now, this is resolved in LES. This is related to the drag by the whole canopy. And this is resolved in LES, and you can say something about how these macro scale roughnesses vary with building geometry. Again, we're going to try to look at this problem by varying lambda p and lambda f as we did before. Now, the problem of Z0m for momentum and the d, which is the displacement height, if you're not familiar with it, this is kind of the actual distance or this is the actual wall that the flow perceives. So if you have a lot of roofs and a lot of ground, the flow sees a wall that is somewhere in the middle between them, and this D is a correction of where the flow actually sees the wall. So what we observe is that actually if you vary lambda f and lambda p together, they go up and they go down, and so this Z0m goes up and down. And the models proposed by Kanda and McDonald actually do a pretty good job in capturing the LES results in green for lambda f and lambda p varying together, for lambda f constant, lambda p varying, and for lambda p varying and lambda f constant. And for D, the displacement height, they do a lesser job, but actually it's still pretty reasonable, and D ends up being not very important for the drag coefficient. So at least the existing model for Z0m and D are reasonably good. Okay. And again, you see that basically when you vary lambda f and lambda p together, the non-monotonic behavior is a result of the superposition of the monotonic behavior when you vary lambda f and lambda p separately. Now, the question becomes what happens to scalars. So you can also define just like you define the drag coefficient for momentum, you can define a heat exchange coefficient for scalars. The momentum drag coefficient varies just like the Z0, it's non-monotonic, decreases with increasing lambda p and increases with increasing lambda f. You would observe that the heat transfer coefficient CH has the exactly opposite trend to CM. So indeed, what's happening is that when you are increasing the momentum transfer, you seem to be decreasing the heat transfer. So there is a somewhat of a if you want a trade-off between momentum and heat transfer. You can then basically measure the Z0s, so the scalar roughness length, and again you can see that scalar roughness length, the patterns here are the exact opposite to the patterns of Z0m. So Z0m was increasing with lambda p or decreasing with lambda p, increasing with lambda f. And if you look at Z0s, it's the exact opposite trend. Now, this is actually good news because typically we try to model Z0S as a function of Z0M. So they could be correlated or anti-correlated, doesn't matter. As long as they are somehow related to each other, I have a good chance of being able to basically model the ratio of the two that is typically modeled in this fashion, where you take log of Z0S over Z0M and model it as a function of P. So I see I'm short on time. I'm going to try to finish in a few minutes. So how do we do that? We tried a new idea related to surface renewal theory. So surface renewal theory is an old theory for how surfaces in the atmosphere or the air exchange scalar, CO2, water vapor, wherever you want, right? So there's a layer of air that is depleted, let's say, in water vapor or heat. It is swept by turbulence to the surface. It remains in contact with the surface for a while, during which it uptakes that scalar. And then it's ejected by turbulence far away, and in that ejection, it transports that scalar far away. So there are two things you need to know to go from this conceptual picture to a flux model. You need to know what is the distribution, the PDF, of the contact time. So how long does this parcel remain in contact with the wall? And so in this case, we're going to model this as an exponential PDF, where R is the inverse of the mean contact duration. And in fact, it turns out that the exact model doesn't matter. It's really this input, the input R, so the mean contact duration is what's important. So even if it's not exponential, it doesn't matter. And then what the other thing you need is, okay, once you know how long it stays in contact, while it's in contact, how fast is it uptaking the scalar? And in that case, you can assume that these parcels are going to uptake scalar again, because it's a scalar, there's no pressure. So it's going to uptake it via molecular diffusion. So you're going to use the solution essentially of an unsteady 1D version of the heat transfer problem. And you can basically replace essentially the flux by Fick's law or Fourier's law and integrate over all contact duration, and then you can get the flux of that scalar. This is the flux in watt per meter square for heat, or in, let's say, kilogram per meter square per second for any other scalar. So the typical idea is that over smooth wall, both the renewal and the viscous diffusion are done by basically viscous scale eddies. So the renewal is done by the little, let's say, worms in the diffusive and buffer layer that are bombarding and renewing the surface. And then the diffusion is molecular. So both of these will scale with Kolmogorov or Batchelor scales. However, for rough walls, the problem is different. So now you have, again, surface renewal, and then you have replenishment, and then you have ejection. But here you can think that, okay, so maybe this micro eddy model still works. So both the renewal time scale and the uptake are dominated by diffusive viscous range scales. So nothing changes. It remains similar to a smooth wall problem. Or you can think that actually similar to what we observed before, when you get a transition to an unobstructed shear flow, the renewal is actually now scaling with a shear length, a shear time scale, rather than with a micro scale. And in this case, basically, you can say that the R is controlled by the shear length, or basically inverse of the shear time scale, while the renewal is still controlled by diffusion. So whether you use the micro eddy model or the macro eddy model, you end up with a model for how Z0S and Z0M relate to each other that depends on the Reynolds number, but to different exponent. In this case, 0.25. With the micro eddy model is 0.5, and this RE star is the roughness Reynolds number. So from our AS, what we can tell you is that, what I can tell you is that it seems that the macro eddy model is the most accurate one. The colored points are the LES, and the macro eddy model is this dot dash, and it matches it much better than the micro eddy model. And this is kind of a similar result from just pure observations here over rough ice in polar regions that also showed a scaling with 0.5. So that's kind of a macro eddy model. However, when we did these studies over smoother lakes and smoother waves, we observed a scaling more with the micro eddy model, again, going towards a smooth wall scaling with RE start 0.25. So let me skip just to tell you that basically whether you agree with the 0.25 or 0.5, the bottom line is both are actually extremely different from how weather and climate model simulate or parameterize the dependence of Z0S and Z0M. Just to close, urban fluid mechanics, a term that is coined by Joe Fernando as the first person to use this, are very important and exciting. And so part of what I wanted to do today is excite all the smart and able people who are on this webinar to basically pick up some interest and start working on this fascinating problem. There's a lot of cool fluid mechanics and turbulence in these problems. To summarize our finding, wall-modeled LES can be a useful tool for explaining UFM. Geometric shape matters. Dispersive fluxes are significant. Momentum and scalars are not transported similarly. And ventilation can be modeled using grants. And so if you want to span all the parameter space of the geometry, you don't need to use LES every time. And so the efforts to parameterize these physics for course weather and climate models that are RANS model, but that don't resolve anything. They don't resolve any building or anything, because the best resolution they get is 1 kilometer. That effort to parameterize these physics is not hopeless. And finally, I have to thank the funders, but mainly the people who did this work. Chili, who's now a professor at Cornell, Maider, who's now a professor at UC Louvain, actually both are assistant professors, and Lucia, who's a postdoc now in my lab, but who's moving next year to Northwestern, and the rest of the team of my lab. And finally, I'll leave you with this cool animation or visualization from a wind tunnel about basically the circulation when you go from flat roofs, which is the beginning of this video. It's going to circulate or rewind to an angled roof to a round roof. And you see that the roof geometry has a big impact. Okay. My computer froze. I don't know if you all can hear me. Let me stop the share. So my computer froze. So I can try to repeat that video. No, I think it completely froze. So let's forget about the video for now. Sorry, I took a few minutes over time, but yeah, if you have any questions, please go ahead.
Thank you so much. No, thank you for the talk. It was very interesting, and we actually got to see the video until almost the end. So that was very interesting. Thank you. If you have any questions from the audience, please feel free to either turn on your microphone and speak up or type in the chat box.
By the way, I should have remembered to do this. I didn't. So let me put in my website and my email in the chat. So if you would like specific details of any of the papers, please email me, or for the papers, you can also go to our website.
Look, thanks very much for that presentation. It was a great presentation, fundamental physics and as well as some applications. So really nice. Thank you. Now, I've got a question about air quality. Indoor air quality is a big deal. And in some places, I'm in Australia, and there are some places here where in relatively surprisingly small towns, urban air quality is very poor in winter due to the use of wood, coal, mostly wood, in indoor heating. And it comes out of chimney typically, but then you have a lot of mixing processes, so that overall urban air quality is very poor. And then you have the problem of ingress of some of that emission going inside the house because you have to have some ventilation. Are you able to maybe just give some insights more generally about any situations like that in relation to air quality, either inside or outside?
That's very interesting. Of course, in winter, it's doubly bad because you use, some burning for heating, and then it's typically cold weather, so that leads to more stable stratification that basically damps the turbulence. So you get a terrible mixture, and then there's less vertical mixing, and any circulation can actually bring the plume down to street level, and that it filters in. So I guess I'm rephrasing what you said, but the bottom line is, I think when you get to these building scale, it becomes very specific. So unfortunately, you cannot really generalize. My only the only solution is to make the chimneys taller. So you can imagine that if you make the chimneys taller, because if I go, let me share my slides again, maybe, and without this video. So you can see, for example, here that when we, let's say you can see here in the mean circulation that we see in this case. Okay, let me go to this one maybe. So if the chimney is very close to the roof, then the pollution from the chimney is going to be swept, and a lot of it is going to be swept down. This is the mean flow, but there's a lot of turbulence. You can imagine at this level that is going to bring the pollution down. Depending on the geometry, but if you lift it a little bit upwards, then basically a lot of that pollution will just skim and continue to go downwind instead of being entrained into the canyon. So the practical solution is to make the chimneys a little bit higher, or to place them differently. But again, you need to do designs that are good for all wind angles and all conditions. So the only thing you can do is just maybe make the chimneys taller.
So in the case of pitched roofs, in Australia, it's not uncommon for chimneys to be mounted midway up the roof, and they do not always exceed the height of the apex of the roof. So in general, maybe at least above the apex would be ideal, wouldn't it?
Yes, I mean, it would be ideal. It's best to do it above the apex. It's actually better to do elevated beyond. Now there's two aspects to this. This is interesting because I've always looked at this video that I was trying to show and told the audience that there's more ventilation with the pitched and round roofs, which is good. But in this case, it's actually the more ventilation is bad, because that's actually bringing pollution downwards, which you don't want. So with pitched roof, you are going to get more mixing, and that brings more, so again, you want to lift it upwards. One interesting aspect is if you have a dominant wind direction, you might be better off placing it upwind than downwind, because when you place it upwind, the flow might basically be lofted, and that might help it not be basically trapped. But again, I guess we need simulation specifically for that case to answer that question more in detail.
Thank you.
While we are waiting for more questions, I may ask a question, just checking whether my understanding is correct, of course. When you showed the results for the aerodynamic roughness, the momentum said null. We basically saw that lambda, F, and P are not changing it much. So does this mean that from the macro perspective, if you're looking at the momentum of the upper flow, the distribution of these elements, whether they are narrow or they're creating more blockage, doesn't really affect it? It's more through the layer within them, the building scale, that we see the impact. Is this correct?
So let me go there and maybe double check. So I mean, this is, are you talking about these graphs specifically?
Yeah, yes.
So this is okay. So this is how Z0M and so Z0M varies with lambda P and lambda F. And what's interesting is this first graph is very common. It basically shows that, you know, you can think if you have 0 buildings that you recover the roughness of the ground. And if you have 100% of building, you recover the roughness of the roof. And in between, you have the peak roughness, right? So this is what this is showing you. But what's interesting in our analysis is that we showed that this is actually a product of these basically opposing trend with lambda P and lambda F. And if you know, in real buildings, lambda F and lambda P might not vary together. So you might be in this situation or in that situation. And here you see that lambda P and lambda F do actually have a big impact on Z0M. So it varies from, you know, 0.1 to or 0.01 to 0.2. Now, bear in mind, we don't use Z0M, we use the log of Z0M. So the actual impact of the log is a bit more muted, but it's still, I would say it's still not non-negligible.
Thank you. No, that makes sense. Thank you. Do we have any other questions from the audience? Amon, do you have a question, or we're gonna wrap up?
Maybe more of an understanding question. I'm not from that background, but I was curious also to know when. So you were looking at isolated buildings, right? If you have now street canyons and aligned in the wind direction, for example, have you also looked into these aspects, whether how they influence the flow structure when you have street canyons, very long?
Yeah. Yes, so we did a little bit of that work, but a nice summary of this. Maybe you wanna maybe look at this this book. This book is on urban climate, so you know, a lot of the people here might not be interested in all its detail, but the chapter on wind flow and wind in urban area is very well done. It's Cambridge University Press book. It's recent, 2020, I want to say, or 2018. So this one, for example, will show you when you have wind blowing parallel or oblique or normal to the wind canyons, what will happen and what kind of flow will emanate. I'm also editing a book on environmental turbulence, and I'm supposed to write a chapter on this topic, but I haven't found the time yet, so it's going to happen soon at some point. So maybe in a year that I'll have my own chapter on this. But meanwhile, my chapter will be mainly about the turbulence, and this is the chapter of Oak is very nice summary of topics related to mean flow and so on. Yeah.
Thank you.
Okay, thank you very much for your talk. It was very interesting, and I'm sure we all enjoyed it. And thank you for your time, and everyone, all the audience, for joining us today.
Thanks again for the invitation and for joining. And sorry if I talked a little bit too quickly at some points. I tend to do that.
No, it was great. Thank you.
Informative, yeah. Thank you.
Okay,
thank you for finding the time as well. Must be very late for you.
No, it's all good. Yeah. Take care. Bye bye. Thanks.
Thank you. Bye bye.